Okay, I hit the wrong record button. Okay, so it fits in 8F squared, and it does not have to fit in the column pitch anymore. Okay, here's the layout. It looks amazingly similar to the open, except for that little jog in the digit line contacts to make room for the adjacent row. I still have the storage node on this side. This is my transistor right here. It's still a 1T, 1C, and it still has a shared digit line contact. Now, this poly 2 storage node by this time is a buried capacitor. And just like we buried photodiodes in the substrate, they're burying capacitors into the substrate. Okay. To actually get the memory cell, all I've got here, since these aren't crossing each other, I can do all the word lines in one layer of poly, and I can do the metal lines in one layer of metal, which is pretty basic processing. Okay. And we'll look at those buried capacitors later. Now, I keep using this word pitch, and I'm going to be using it over and over again. If we look here, the digit line pitch between these metal lines is 2F. And the word line pitch is 1/2 to, no, I thought it was frozen. 1/2, 1.5, 2.5, 3.5, 4. It's the word line pitch is 2 times bigger. Any time I have a circuit that's driving something on the column, like the column decoder or anything like that, or the sense amp layout, it's got to fit in that width one column. And that's what I mean by pitch. This is as far apart as the array is. This is as far apart as any circuitry that connects to every column line in the array can be. In the word line, it's a little bit more relaxed. I can make it 4 features wide. Now, when we were building our detector arrays, we made a A to D converter. It was a 10-bit A to D converter that had to fit in the column pitch. It was, and I'm not making this up, it was 10 micrometers wide and about 2 centimeters long. So that 10 micrometers between the pixels, you could not deviate from. You had to make it long and skinny. So there's a lot of long and skinny electronics going this way for the drivers. You try to keep the driver electronics as simple as you can. Okay. Do we want to minimize the pitch or do we want to maximize it? That's a good question. We would want to minimize it because we want to make the memory erase die as small as we possibly can. But then again, in order to fit the readout circuitry in there, we would want it to be maximized. So it's a trade-off, and you have to figure out, what's best at that given time.
I guess we just have to make the readout circuitry smaller.
You'd have to make the readout circuitry equally smaller, and you'd have to make it long. You might have to make it long and skinny, like that 10 micrometer by 2 centimeter A to D converter. 512 A to D converters in parallel. The transistor drive. Well, the transistors that are driving this line, the buffers that are driving this line, ideally you want to have a high current drive so that they can drive the whole length and the capacitance and the RC delay of that line as well as fast as they possibly can. But again, to make that drive bigger, you've got to make the buffer physically larger, and you have the limit that it has to fit into the column pitch. A lot of trade-offs. The transistor to transistor leakage, you want to make this as small as you possibly can. If current from this transistor is conducting in this transistor, if these two are sharing current, if there's leakage current going through there, I could be charging or discharging those capacitors without actually wanting to. So we want to minimize the leakage. And I won't tell you why, but that's the reason why that bottom plate of the capacitor is at VCC/2 and not at ground.
And leakage in general is just bad to have.
Yes. It has to do with the body effect.
Oh no.
We're making the body effect bigger purposely by running the capacitor, bottom plate of the capacitor at VCC/2, which makes the threshold voltage larger, which means there's less leakage. We're doing that on purpose. The cell capacitance, remember, whatever the in-bit cell capacitor is, has to drive the digit line capacitor, which is already, and this is VCC/2, which is already fairly big. So we want to make that in-bit capacitor as big as we possibly can. And that's the reason why they're driving those fingers down into the substrate, making them go up and down and around and being very narrow spacing in between them. Which, of course, doing that makes the yield lower. As a PUP engineer, you get like one tiny little part of this, or you've got, or you become a product engineer, or you become a test engineer where you're looking at one little piece at a time. Don't get overwhelmed. There's a lot here, and this is why there are thousands of people working at Micron. Each one has their own little specialty. You don't have
all cogs in the great machine.
Yes. And it takes them all. Okay, so this is the open architecture. We've talked about that a good bit. This is a new one, and it's called bi-level plaid because it looks kind of plaid-y. I don't want to draw the schematic for the bi-level plaid because it's on the next slide. Okay, there it is right there. Basically what I've got, what I want to do here, why it's called bi-level. What I want to do here, I've got the column line from one, I've got the column line right here, and I've got another column line, we'll call this column line 0, I'm just making the names up, we'll call this column line 1. And they run adjacent to each other. They found that if I twist, oh, you guys know about shielded twisted pair? Probably not. You may have seen it before, but you don't know why. A lot of audio circuits, if they're not using coax, will use this thing called shielded twisted pair, where you've got the hot line, the red line, and you've got the ground wire, the black wire. And what they do is they just twist them around each other. And that's a really bad drawing. Okay. But they take the two wires and they just twist them together. and they form this helix. Why does anybody bother to do that? Okay, what happens is with radiation and electromagnetic interference and pickup, let's say I have like a radio transmitter over here. If the two lines are running parallel to each other, this line is always going to get a stronger field from that source than the other line. And you can actually see the difference. If I look at the signal on here, I'd see a larger signal, and up here, I'd see a smaller version of that signal. What I want ultimately is I want the same garbage on both lines. And if I get the same garbage on both lines, I'm going to be able to reject that with a good difference amp. A good sense amp is a difference amp. It's amplifying the difference between the two signals. If they both have the same junk on them, then I can reject that noise. If they have different junk on them, I can't. So if I twist these wires together, if I do this, the red line's going to be closer to the source sometimes, and the black line's going to be closer to the source sometimes, and they get the same junk on them. So now red and black look pretty much the same. It seems like black magic, but it works.
So it's just for noise reduction, or?
Yes. Okay.
Well, if it reduces noise, then I suppose that, yeah, pretty good.
Okay.
Yeah, even if it's black magic, but 60% of EE is black magic, so
Yeah, it is.
Witchcraft.
They teach you the math, and they think that's important, and then you have to make things work. So
Just
what?
throw numbers at the page.
Throw numbers at the page. Or let's just change this resistor value until it actually does work, and then we'll talk about how smart we are.
Trial and error.
There's a lot of that going on too. Okay, so what they're doing in this bi-level plaid is column 1 line is going through here, but when it's going to do a twist, and they're going to change positions. Now this becomes column 0, and this becomes column 1. And then we go through another way, a little bit in the array, and we're going to twist them again. It's the same thing as twisted pair. And the way they do it is they run one in metal 1, which is like the first story of the building. And they run one in metal 2, which is the second story of the building. And then they switch stories. And we'll have diagrams of this later. Okay. So this is how engineers truly think. This, with no twist, worked for a while. If I do this standard single twist, it works a little bit better. What if I twist it a whole bunch of times?
It's very twisty.
We get very twisty. I'm going to twist it more often. I'm going to alternate twisting on this line with where I twist on the odd lines with where I twist on the even lines. And I'm just going to vary the twisting schemes. I can have more complex twists where I've got going from here, I cross across these 4. There's all kinds of things you can do. And I'm sure what they did is somebody came up with a brilliant idea. They ran something through their engineering line and to see if it worked and if it really made a difference. And if it did, then they tried to make the twisting more complicated. And then they repeat that.
So is the triple modified twist the most efficient one, or?
That's as far as they got on there. I don't know what they're using today.
Okay, because in the pre-lecture I guessed it was the complex twist because I thought it looked the coolest.
Right. Okay. Yeah. I couldn't tell you off the top of my head. I'd have to like dig through the book. Okay, so that's twisting. We will have diagrams at some point in this class that show you exactly how they twist the metal layers, because they have to do it without shorting between the metal layers too. So instead of going between metal 1 and metal 2, they may have to put a third layer of metal in there and have go like do this. Metal 3, let's see if I can even do this. Metal 1, and then you have metal 2 here. And what I do is I drop a via down to metal 1 for this one, and then I would have to take this one directly up to metal 3, and then I could drop this down to metal 1. There's things like that. They have to go through a whole bunch of via networks. It takes up space. And at some point, the efficiency, your signal to noise ratio doesn't improve anymore compared to the extra gaps you have to put in for twisting.
So, with like the no twist, are those, is that like one layer on top and then you have a second layer with like the arrow going to the right?
Well, without the twist, I could run everything on metal 1 because they aren't crossing each other. This is when I start twisting, I have to put different metal layers on here because I'm going to have to jump this up to another metal layer to go across there.
Oh, okay.
Yeah, to keep them from shorting out.
And so the more you twist it, then I assume that it allows you to basically put more stuff in a confined space. Then my hand is being slowly eaten by the background.
Yeah,
but
it takes space for the twisting to happen, and it's space that you can't put memory cells in. So you're actually going to lose usable area doing this. But if you can increase your signal to noise ratio, then maybe I can make the cells smaller. And they keep on making them smaller and smaller. So here's the first attempt at a buried capacitor. Basically what they've got here is they've got, let's see, there's the active area. Here's the digit line contact coming in. I'm just trying to orient myself. This is the digit line contact. This is the poly word line. So this is the transistor part. We'll just label this T for transistor. Here is the, and this is like down into the substrate. Okay. Here is the contact for the poly. I've got the storage node right here. And no, it's not down. This is actually not buried. I take that back. This is above. The capacitor is above the substrate. So I've got a dielectric here, and I'm building my capacitor right through here. It's being built above the circuit. Not a lot of area for our capacitor. This is one plate of the capacitor. Right there. This is the other plate of the capacitor, and this is the dielectric. So not a huge amount of area. Now remember our big rule for capacitors, C equals, I forgot to put the epsilon first, sorry, epsilon A over D. So I either make it thinner, I use a stronger dielectric, or I put a bigger area in there. This would work, this is on a micrometer scale. So we're talking about, you know, maybe like a micrometer process. You could get away with doing stuff like that. I could skew it slightly. This is as we get further into this. What they're doing is they're making the capacitor longer. They've got the processing technology to do that. The capacitance is actually, they've got layers in here. There's this is the dielectric, this is conductive, this is conductive. So that's the capacitor, and they've got 2 fingers for this capacitor, and they're starting to bury it into the substrate. Still on a micrometer scale. This was what they were doing up until about, well, they're still kind of doing it now. This is called a trench capacitor. This is kind of what they're doing recently, as recently as I've talked to them. I've got the poly storage node is conductive. I've got a very thin dielectric layer here, the ONO, and I have the heavily doped substrate region is also conductive. So I've got a very narrow capacitor in that region between the dotted line and the solid line in there. So again, it's epsilon A over D. We've made D really thin. We've made D very small, and we've made A larger by making it 2 times the length of that thing. Now they're burying them deep into the substrate. This is like 1 micrometer, so you're looking like 10 micrometers into the substrate. Kind of like my nightmare scenario for micron. How do you keep these things from shorting out? And they do. And there's defects, where places where capacitors short out, bad memory cells. They map them out of memory logically and don't use them. How do I, and the area, because I've buried it tens of micrometers down into the substrate, I've made A big. And then I work on the dielectric strength of the material. Can I get some kind of exotic material in there to make epsilon higher? They keep trying to make that capacitance bigger and bigger in order to get bigger capacitors in smaller areas, so they can get some actual signal on the digit line that they can compare in the sense amp. Okay. Wow, I haven't crashed in about 10 minutes.
Don't jinx it.
Boom, right? That last time my computer wouldn't turn off either. Now and all of this is stuff we're going to be talking about all semester long, but we'll just go into a little bit more detail. This is like the Brouwer theory of education, where you cover everything thinly and then you go into detail on a lot of the subjects. So we're going to talk about the equilibration circuit. This is one of the circuits you need to build for your project. We'll talk about I/O transistors, and we will talk, this is the sense amp. We get to talk about latches today and isolation transistors. This is the equilibration circuit. Put a little star or something in your notes, slide 7, number 7, slide set 2, slide 22, whatever you want to do. It's also in the Keith book. 3 transistors. First step is I pre-charge these lines to VCC over 2. I've already warned you, do not put the slash in the name in Banner Graphics. Call it VCC2. What am I going to do with M1? One of these lines is going to get signal on it. So let's say this one becomes VCC over 2 plus signal, or no, not yet. Okay. Stop. Start over again. Okay, this stop. Okay, the purpose of this circuit is to pre-charge the digit lines to VCC over 2. They're not pre-charged already. One of them may be sitting at 0, but they could both be sitting at 0. One may be sitting at 0 and one may be sitting at 1. Whatever's going on. I put M1 in. It's called a pass transistor. If I turn the gate on of a transistor, what happens is the drain and the source are going to want to go to roughly the same voltage. M1 provides a path for charge sharing. Sharing begins with an S.
Charge gearing?
It provides a path for charge sharing between the two of them. M2 and M3 are tied to the drain is already tied to VCC over 2. When I turn equilibrate on, they're going to act like pass transistors. M2, we'll call this a source. The drain of M2's, since this is hard tied to a supply, is going to want to try to pull whatever this is to VCC over 2. This is also a pass transistor. And this is oh no, oh, just my pencil's not working. Just my pencil's not working. Oh, great.
Technical difficulties.
Why can't I make a B? Let's just change the color. I change the color. Aha. I don't know. I push enough buttons, it works. Okay, so these two transistors are going to want to put VCC over 2. Oh, great.
Did you freeze again?
No, I did not freeze. My pen froze. I got a new battery. Okay, now it worked. Now it's working. Okay. It's going to want to put VCC over 2 here. And I get VCC over 2 here. And any charge that needs to go back and forth is going to go through this M1 transistor. So there's the equilibration circuit. This is a clock. When I want to equilibrate, when I want to drive all those lines to VCC over 2, equilibrate will be true. So when equilibrate goes true, whatever's on the other 2 lines suddenly goes to VCC over 2, and it will stay there even after I turn equilibrate off. Okay. This is how I lay it out. If I want to read a layout, this is the way I do it. I look for labels. This one's labeled VCC over 2. Here's a contact, and this one is tied through the contact to D. So this must be D. This is tied through the contact to D star. I look for my poly lines because my poly lines are where the transistor is. A transistor that's tied to D star, and the other side of the transistor is going to VCC over 2 is M2. So this region right here of the poly must be M2. The one that's going between D and VCC over 2 is this region right here. That must be M3. And the one that's going has the drain at D star and the source at D. This must be M1. So it's a fairly simple layout for the equilibration circuit. And if you don't believe, and then on the next slide, I basically just did that. There's the transistors. The guys that do layout are geniuses of fitting, what what do we call, what's a nice way of saying this? They're really good at putting 10 pounds of stuff in a 1 pound box.
They're very good at packing things away.
Yeah. The guy who designed our Pixel for our photo detector arrays, he'd come up and he would say, okay, he'd start out, go, the Pixel's 20 micrometer pitch. Okay, Guan, we got it. And then like a week later, he'd come and go, you know, I figured out something. I can make it smaller. It's on a 15 micrometer pitch now. Oh, good. And we never questioned him. And, you know, like a week or two later, 10 micrometer pitch. So they just.
You have a question in the chat, Julie.
Oh, okay. Oh, great. I have to find the chat.
I can just read it to you.
Or would you mean PCB board, Josh? Okay. The best we've got here right now is my 490 in the fall. You get to actually do a simple PCB layout. And I talk about PCB layout from the point of view of not as a technician doing PCB layout, but more as an engineer. What are the important things to look for, the crosstalk and the signaling and keeping your signal integrity and those kinds of things. And there's a bonus assignment to actually route a PCB. And it's a good skill to have. There's a lot of jobs out there. I try to squunch analog and PCB layout all into one little thing. Given one class, all the things I thought the students should know that they don't.
It was a really fun class.
It is. It's more fun if you can actually be there. There was a lot of lab work normally. We had to go like, I had to just talk more. Okay. I get these data lines coming from, and these are coming from the column. So the column line D0. What I want to do is when column 0 is selected, C select of 0 is true, I turn on the transistor from D0, and this is acting as a pass transistor. So if this column select is true, whatever's on column 0 now goes out to IO line A. I don't have as many IO lines as I have column lines. Those are the things that are going to ultimately go to the buffer that I put at the end to spit the data out. So when this column's selected, I want the data from D0 to drive the IO lines. Multiple things can tie to that same IO line, and they will. This is just another step in getting them out of the array.
Hey, just to let you know, you've got 10 minutes left, Julie.
Thank you. I've got lots of slides. Oh, the sense amp. Okay. Oh, but this will go fairly quickly. This is what I want to build. I want to build the D latch. Okay. We'll call this inverter 1 and we'll call this inverter 2. The standard way of doing this, like in a CMOS SRAM cell, is I've got, let's call this is the input of 1. N1 is this line right here. It goes into, this is part of inverter 1. This is part of inverter 1. The output of inverter 1 is right here. That's out 1. And it goes back and it's connected to the input of 2. So the output of inverter 1 is connected to the input of inverter 2 and vice versa. It's a standard latch. This is what I'm doing with the sense amp. It's the same thing, it's just drawn a little bit different. The lines are crossy. It looks like a latch. One of the big differences is this is at VCC, the power supply is at VCC, and the other power supply is at ground. I've got a new name. These are actual signals. All ACT is the VCC power supply for my sense amp. All NLAT star is the ground for the sense amp. The only reason why I have these differently named signals is I don't want to power up the sense amp unless I'm using it, because it's going to waste power. So I turn it on when I need to sense something, and I turn it off when I don't. I've got a switchable power supply on there now. So here's my basic sense amp block. I'm going to put D0 on one of the lines and D0 star, what I'm comparing it to, on the other. I've got my power supplies, my positive and my negative power supplies right there. I'm going to take that inverter thingy. Did I just do that? Yeah, I did. Okay, pretend like that bubble's not there. This inverter thingy, and this is basically where D0 and D0 star are going. Now this thing has two stable states, D0 is high and D0 star is low, or vice versa. If I have a very small signal in between there, it's gonna, well, it's like a latch. If I have, this one's a little bit higher, it's gonna force this side high. If they're both at near VCC over 2, whichever one's a little bit higher is gonna force that state to be high. It's acting like a comparator. Now the timing for this, I've got, let's say D0 star is initially at VCC over 2. D0 is VCC2 plus a signal, which is greater than 0. NLAT star is going to normally be, when this thing is off, is going to be sitting at VCC2. I pull it to ground first. Okay. When I pull that one to ground, M1 is going to conduct more than M2 because D0 is greater. And then the next thing that's going to happen is ACT goes up to VCC. So we turn on the latch completely. Now M4 and M3 get involved, the PMOS transistor. M4 is going to conduct a little more current, and it's going to pull it into that stable state where D0 is going to go all the way up to VCC, and D0 star is going to go all the way to ground. And I'm back in the stable latch state. That's the basics of the sense amp. And do I have enough time for this? Maybe. Inside the sense amp, I'm putting the P side of the latch, the N side of the latch. I'm putting my equilibration circuit in there. I want to put the IO transistors, and I'm going to put some isolation transistors in here. So this is the standard sense amp, and this may be as far as I get. I have the P side of the sense. I've got 2 of them because we all know PMOS are far inferior transistors. They're slow. They don't conduct a lot of current. So I'm going to double up my P sense. I've got a single N sense. And I read the labels, that always helps. I've got an equilibration circuit on this side. I've got an equilibration circuit on that side, just to make sure that both sides of the bus equilibrate. And I can actually turn one side of this off and have it still work. I've got the IO transistors here. We talked about those. Reading the labels really helps. And I've got some isolation transistors. When I turn these transistors off, this side of the amplifier is isolated from that side of the amplifier. So I can choose between looking at the array 1 side only, the array 0 side, or having them both connected at the same time. Right, we just did that. Read the labels if you want to know what the circuits are. I think there's something like that on either an exam or a homework. This is the labels. Go through these fairly quickly. Standard sense amp we've already talked about. Sometimes they need to make the sense amp smaller, and sometimes they need to make the sense amp have better performance. So these are all different kinds of sense amps they put in production, and thank goodness I labeled these. What I've done with this one is I've made the isolation transistor network a little bit more complex to get better isolation. I got rid of one of the P-Sense amplifiers to make it smaller. I only have one equilibration circuit and I only have one P-Sense. I've made it even smaller. This is the minimum sense amp. The one you're going to build for your project, like project 3, is the standard. I could do this in a single metal layer by moving the P-Sense amplifiers to the other side of the array with their P-wells that take up a whole bunch of space, so that I can route this all in NMOS without P-wells and make it even smaller. I think I'm just about done. Yeah, and we talked about that. And I'm done. If anybody has any questions, I'm done on time by some miracle.
It's a Christmas miracle.
Did Matthew Miller ever show up? And the 2 kids in China who will probably watch it on video. Xu Jian and Yu Hao. Okay. Any other questions?
Julie, can I schedule a meeting with you on Monday, because there was a thing on the homework that confused me, and I'll wholeheartedly take a low grade in the homework. I just want to know how to do it.
Okay, no problem. I will be in my office on Monday, generally from about 10:30, depending upon how lazy I am, to 4, and then I have class.
All right, sounds good. I'll contact you at some point in that time frame.
Okay, all right.
Thanks, Julie.
Okay, I'll see you.
Need to go run around and burn off some of this caffeine energy or before Cambo's, or else I'm gonna die.
Yeah, I had to call. I had to call Vitaly in because I couldn't do my homework for 310. And it was an OR gate. He couldn't figure it out either, so I felt better. But finally, we have an OR gate. Okay.
Have a good day, Julie.
I'll see you.
Have a good weekend.
Okay.
Hey, Julie, can I ask you a quick question?
Sure.
Since I joined late, will I have any opportunities by any chance to make up all the work that I missed, or is that just out of the books?
No, go ahead and do it and just email it to me instead of going through the submission link.
Okay, awesome. And do I have a deadline on that?
Yeah, we try to do it by Monday.
Okay, that's perfect.
Okay.
Sweet.
What-
Anything else that I need to do?
What is your NAU email?
It is N as in
Nolan.
TM
Wait, N what?
as in Nolan, then PM as in McNeil.
Okay.
MCNEL.
Right.
53.
53. Okay, because I just need to get you added onto the team list. If I don't tell you, we're going to assume right now. Oh, great. Your team number. I'll email you and tell you what your team number is.
Okay, awesome. I appreciate it.
Okay, great. I'll see you.
Okay, have a good one.
Okay, bye.